Measurement is kind of like a universal language. It's what science speaks, what cooking speaks, really what almost everything speaks. And just like any language, it's got its own grammar, its own rules, its own little quirks. So let's get into it. Let's crack the code of measurement together.
Okay, so think about this for a second. Have you ever been baking and the recipe calls for, say, exactly 125 grams of flour, not just a cup? And you're wondering, why so specific? Is it just being picky? Well, no. It's all about speaking that language of measurement with fluency. It's about precision, and we're about to learn how to translate it.
All right, first things first, we need to get two very important words straight: accuracy and precision. They sound similar, but they're totally different. Imagine you're throwing darts. If all your darts hit a tight little cluster, but they're way off in the corner of the board, that's precision. You're consistent, but you're wrong. Now, what if your darts are scattered all over the place, but they're kind of centered around the bullseye? That's accuracy. You're right on average, but you're not consistent. What we're always aiming for, though, is to be both accurate and precise, hitting that bullseye every single time. And here's a non-negotiable rule. Every single measurement needs a unit. I mean, think about it. If I just say 32, what does that even mean? It's nothing. Is it 32 degrees? 32 feet? 32 miles per hour? See? The number tells you how much, but the unit tells you of what. Without it, we're just talking nonsense. Okay, so let's start cracking this code by going back to the classics. We're talking about analog tools, rulers, beakers, that kind of stuff. This is where the real skill comes in, where we learn the art of the estimate.
And there's a golden rule for this. I mean, this is the rule for reading any analog tool, so listen up. You always estimate and report one decimal place beyond the smallest little line marked on the device. That's the secret. It's how scientists, and now how you, can show exactly how good your measurement really is.
So let's put this rule to the test, shall we? Take a look at this object on the ruler. Your turn. Based on what we just learned, what's your best guess? How long is it? Okay, let's break it down. First, what are we looking at? The big numbered marks are centimeters, and all those little lines in between, those are millimeters, which are tenths of a centimeter. So the smallest division is the tenths place, right? Our rule says we have to go one step further. We have to estimate to the hundredths place. Which brings us to our answer, drumroll please, 7.85 centimeters. See how that works? We know for sure it's past the 7.8 mark, but it hasn't quite reached 7.9. That last digit, that 5, that's our educated guess. That's our estimate. It's not just a random number, it's a statement. It says, this is how precisely I can measure this. All right, round 2. Let's try another one. This time, we've got a graduated cylinder with some liquid in it. Take a look. What do you think the volume is?
But wait, before you shout out an answer, there's a little trick when you're measuring liquids like water. You see that curve at the surface of the water? That has a name. It's called the meniscus. And the rule is you always take your reading from the very bottom of that curve. If you don't, your measurement's going to be off.
So if we look right at the bottom of that curve, we can see it's clearly above the 42 line, but it's not quite at 43. Now, the marks on the cylinder are for every 1 milliliter. So what does our rule say? We estimate to the tenths place. My eye tells me it's about 42.8 milliliters. And again, that 0.8 at the end, that's our honest estimate. That's us communicating the limits of our tool. Okay, that covers the old school analog tools. But what about the digital stuff we use every day? You get a nice crisp number on a screen. That must be perfect, 100% certain, right? Well, you might be surprised. So before we jump to a digital scale, we have to clear something up real quick. It's a classic mix-up, mass versus weight. They are not the same thing. Mass is the actual amount of stuff in an object. It never ever changes no matter where you are. Weight, on the other hand, is just the force of gravity pulling on that mass. So your mass is the same on Earth and on the moon, but your weight? Totally different. And that brings us to the modern electronic balance. Now, funny enough, it's actually measuring weight, but it does a quick calculation to show you the mass. But here's the kicker. If you've ever used one, you've probably noticed that the very last digit kind of flickers a bit, right? It can't make up its mind. That's the machine literally telling you, hey, just so you know, this last number, this is my estimate. This is my uncertain digit. All right, so we're getting pretty good at taking a single solid measurement. But what happens when you need to talk about that measurement in a different way? We need to talk about conversion. And don't think of it like boring math homework. It's more like translating between different dialects of the measurement language.
Let's go back to our ruler measurement, 7.85 centimeters. What if we need to express that in meters? It's pretty straightforward. We start with what we know, 7.85 centimeters. We also know the conversion fact, or the equality. There are 100 centimeters in 1 meter. So we just do the math and boom, 0.0785 meters. It's the exact same length. We're just speaking a different dialect.
All right, we've come to the final and maybe the most important piece of the puzzle. This is what I'd call the grammar of measurement. It's time to talk about something called significant figures, or if you want to sound like a pro, just call them sig figs. So what in the world are sig figs? It's actually pretty simple. Significant figures are just all the digits in your measurement that you're absolutely sure about, plus that one estimated digit at the end we've been practicing. That's it. You could call them the honest digits, because they don't pretend to be more precise than they really are. But why do we even need this rule? I mean, why does it matter? Well, take a number like 150 centimeters. What does that 0 mean? Did you measure to the nearest 10 centimeters and the 1 and 5 are the only real digits? Or did you measure exactly to 150 and that 0 is just as important as the other numbers? You see the problem? It's ambiguous. And if there's one thing science can't stand, it's ambiguity. And that's why sig figs have grammar rules, especially when you start doing math with your measurements. For adding and subtracting, the rule is simple. Your answer can only be as precise as your least precise number. It's like a chain. It's only as strong as its weakest link. So if you add a super precise number, like 15.303, to a less precise one, like 1.0, your answer has to respect that weaker measurement. You have to round it. It's all about being honest with your data. And really, that's what this all boils down to, isn't it? Good measurement isn't about getting the right number. It's the art and the discipline of being totally honest about what you know for certain and, just as importantly, what you don't. So, at the end of the day, what's the big takeaway? Measurement isn't some dusty thing for scientists in a lab. It's a powerful tool for every single one of us to make sense of the world. Now that you know the basics of the language, now that you can start to crack the code, I'll just leave you with one final thought. What's something you could measure today to understand your world just a little bit better?